Hello everyone, my name is Simon from Wageningen, and together with Tamara Mchedlidze and Alexandru Telea, we've explored how to identify cluttering edges in near-planar graphs. To start off, when we say planar drawings, we mean node-link diagrams that have no edge intersections. For these types of drawings, we know the following. We know that users tend to prefer planar drawings over non-planar drawings. Purchase, for instance, also showed that the fewer crossings a drawing has, the better the performance is of users on certain tasks. Additionally, we can also test planarity and subsequently construct a planar drawing in linear time. The problem, however, lies in the fact that graphs themselves are rarely planar and rarely admit a planar drawing. But we do observe that when graphs are sparse, they can have a planar substructure, such as the example graph here. So then the question becomes, can we create near-planar drawings? And this question has been explored multiple times before, in both a theoretical and practical manner. For instance, there are plenty of edge insertion approaches, where edges are inserted into planar drawings in a crossing optimal way. There are also specific approaches such as the right angle crossing, the alpha angle crossing, k-planar, quasi-planar drawings, and finding the maximum planar subgraph. However, all of these approaches suffer from some tough computational complexities. On the practical side, there are a few algorithms that can indirectly be used for near-planarity purposes. Stress majorization, for instance, is a spring-based layout algorithm. Gansner et al. Also describe in their paper a way to weight edges by their shared neighborhoods, thereby allowing for longer edges to exist. Similarly, Simonetto et al. Developed a force-directed technique called impred, which simply improves a layout while preserving edge crossings. Kruiger et al. Showed that with TSNet, that the TSNE projection technique could be used to construct high-quality graph layouts, with the option to allow for longer edges to exist. Lastly, Force Atlas 2 is a highly popular layout algorithm not specifically used for planar layouts, though it tends to create fairly decent drawings in general. The problem here, however, is that none of these techniques directly focus on bringing planarity forward. And that is where our initial experiments comes into play. Consider a simple drawing of a grid drawn by Force Atlas 2 here. So let's put a few edges on top of this graph and redraw it again. These problematic edges distort the layout and obscure the underlying planar substructure. Now, here we directly know that the edges we put on top distort the layout and create clutter. So what if we simply weight these problematic edges with an arbitrarily low weight? If we do that, then we get the following layout. The original grid-like structure is unfolded and is much more apparent than before. So then the question becomes, can we directly find these planarity-destroying problematic edges? However, before we move on to that question, we would like to highlight a very different experiment that we briefly conducted. We created triangulation graphs, which were simply constructed by putting random points on a 2D plane and then doing Delaunay triangulations on those points. We noticed that when we used Force Atlas 2 or stress majorization on these triangulation graphs, that they tended to create quite a bit of clutter in the outer faces of these graphs. So therefore, we slightly adjusted our research question to the following. Which edges of a given nearly planar graph G create clutter in the drawings of G generated by a spring embedding algorithm? To try and answer this question, we developed a heuristic consisting of two simple steps. First, we find an identifier for each edge, and then we classify and weight the anomalous edges. To find an identifier, what we call a footprint, for each edge, we take a look at the maximum number of vertex disjoint paths, which we can simply get using the MaxFlow Edmonds-Karp algorithm. Let's consider this grid, and specifically, let's look at edge AB. The very first, shortest path would be to take this long edge from U to V, and the next ones would be this black path, and similarly this black path. Lastly, this orange path is the last possible vertex disjoint path. We can already see that these paths are relatively long, and this becomes more apparent when we take a look at the rather simple edge CD. Here, these two green paths are the first vertex disjoint paths, And after that, we only have these two black paths left. So when we put these path distances into numbers, we can already observe the differences between the edges AB and CD. From these numbers, we can thus construct a footprint which can serve as an identifier for edges. Now, to find which edges are different from others, we use the isolation forest technique to classify the edges based on their footprints. And this technique is relatively simple. In this example here, we have two-dimensional data points. For each point, the technique tries to isolate the data point using random cutoff values in a single dimension. So let's say we create a random partition on the y-axis here, and then on the x-axis, and then on the y-axis again. We've now isolated the data point in the circle here using only 3 random partitions. We now repeat this partitioning process for every data point, then repeat these processes numerous times in order to get an average number of partitions. The average number of partitions for each point simply indicates how anomalous a data point is. After we standardize our footprints, we simply apply the isolation forest technique and subsequently weight the edges classified as anomalous based on their footprints. To test the effectiveness of our heuristic, we apply it to 4 datasets: augmented grids, augmented triangulations, deep triangulations where we simply have a fraction of the nodes inside a triangle, and Rome graphs. We use Force Atlas 2 and stress majorization to create layouts. As with these algorithms, we can easily adjust the weight of the edges. Additionally, we also compute 4 quality metrics for each layout. Firstly, the angular resolution, which is simply the smallest possible angle between any 2 adjacent edges. The crossing resolution, which again is the smallest possible angle, but now between any 2 crossing edges. The number of edge crossings, which speaks for itself. And lastly, the procrusted statistic, which measures how similar 2 drawings are, taking the rotation, the translation, and scaling into account. It's a measure for similarity. On the left here, we have the original layout of a deep triangulation graph. On the right, we have the layout where edges were weighted by the heuristic. Immediately, we can spot some differences, most notably in the outer face over here. The layout is still far from perfect, but there are visible improvements. For Rome graphs, the heuristic has a tendency to create long edges leading to unbalanced layouts. One could argue that the layout produced by the heuristic has a lower quality. However, we've noticed the biggest improvements in experiments done on the grid graphs. So again, the layout where the graph was not weighted is on the left, and the layout of the weighted graph done by the heuristic is on the right. The heuristic here has allowed the layout to unfold again and bring back this grid-like planar substructure. We've also noticed similar improvements in the triangulation graphs. Again, improvements in the outer face as well as a much more visible planar substructure. When we take a look at the quantitative results, we would like to highlight the number of crossings metric. We mainly look at the results from Force Atlas 2 here, because the differences between Force Atlas 2 and stress majorization were rather minimal. In this figure, here on the y-axis, we have the number of crossings. In red, we have the triangulation graphs, and in blue, the grid graphs. Here, we're simply comparing this redraw column, which represents the redrawn layout with the cluttering edges on top, and with the layouts produced by the heuristic hmin, hmax, and hmean. Here, the min, max, mean simply indicate which function was used to weight the anomalous edges. The horizontal black bars represent the median lines. From these distributions, it is clear that the heuristic produces drawings with fewer number of crossings compared to the unweighted graph layouts, and this difference is statistically significant. We also see a similar statistically significant difference for the procrusted statistic metric. Here, the layouts of the heuristic are much closer to the original layout than the redrawn layout, meaning that the original structure is much more visible for layouts produced by the heuristic. Additionally, We see a similar pattern for the number of crossings for deep triangulations. However, for the other metrics, there are a few significant differences across the graphs and techniques, but we do want to note that the layouts produced by the heuristic for the Rome graphs tend to have statistically significant worse results for the crossing resolution and the angular resolution when you compare the new layouts to the original. To conclude our work, we've created a heuristic that can detect cluttering edges in near-planar graphs. Using the heuristic, we can produce higher quality near-planar layouts, though the graph class heavily impacts the effectiveness of the heuristic. In the future, we would also like to look into testing the heuristic on real-world graphs, as well as making additional comparisons with the TSNet technique. And lastly, we do see the threat of the large computational complexity we have of the individual components in our heuristic, and this is definitely something that could be improved. Thank you for your attention.